Hello, this is Truth Socrates. Welcome to our 8th video in this series for Multivariable Calculus, Math 5C at Pasadena City College. So in our previous video, we did a review of the definite integral. It's the limit of a Riemann sum. And we said that basically it represents an area under a curve if your function, of course, is positive over your interval of integration. We also interpreted definite integral as a density function, which when integrated over our interval will give you a total mass for a piece of wire, which we pretend is living on that interval. And finally, we saw how to generalize the definite integral in almost any scenario. Okay, so the several integrals that we're going to create in this class will all look like this. You have an integral symbol, or maybe there will be 2 integrals or 3 integral symbols there. You have a function, and then you plug in a point in the domain for the integral, and then you have a differential here. Okay, so we said that the basic steps to find or to define this general kind of integral is, first we subdivide our domain D into several pieces, and then we find the measure or the size of each piece. Okay, so in the definite integral it's a width, but today we're going to create an area, and later on we're going to look at volume or arc length or surface area. So it all depends on the geometry of your domain. Now, in each of the little pieces that we chop up our domain into, we will choose a representative point, a special point in that domain, and then we will form the Riemann sum of this function f evaluated at these representative points. We're going to multiply that value by the size of each subpiece. Okay? And then we're going to take the limit of this Riemann sum as the number of pieces goes to infinity. Okay, so it's always this limit process that's mysterious. Okay, I'm sure you had a little bit of a challenge understanding that in basic calculus. Okay, but of course, after we create these integrals, we're going to find ways to compute them exactly, much in the same way that we have the fundamental theorem of calculus in basic calculus. Okay, you look for an antiderivative, you plug in the endpoints, and then you subtract, right? So let's do these steps to create our double integral over a rectangle. All right, so here's the setup. We have a continuous function f of xy, which is defined on a rectangle. So we write the rectangle R as the interval a to b crossed with the interval c to d. Okay, what does that mean? All the points xy on the partition plane where x is between a and b and y is between c and d. Okay, so we have this diagram down here. Okay, so x is going from a to b, y is going from c to d. So this is going to be the domain of our double integral. Okay, so let me scoot up over here. We want to create the double integral over this region, this rectangle, of our function of 2 variables, and our differential is symbolized as dA. Okay, so we'll explain what that dA means in a little bit. All right, so for the basic definite integral, we divide the domain from a to b into several pieces. So let's call those number of pieces m. We're going to do it again for this rectangle, but of course, it's not just the x interval that we're going to subdivide, it's also going to be the y interval. Okay, so I kind of think of it as like a birthday cake. Okay, you have several guests at your party, so you want to make sure that each guest has at least a little piece. Okay, so here, what do we have? 1, 2, 3, 4, 5, 6. Okay, so we have divided A to B into 6 pieces. And then how about C to D? 1, 2, 3, 4, 5. 5 pieces. Okay, so we divide C to D into n equals 5 pieces. Right? So of course we've seen this formula for delta x. There's a similar formula for delta y. Okay, the endpoints are d and c, so we have d minus c divided by the number of pieces n. Okay, so in the single integral, it was n that we used for delta x. Okay, but since we have 2 now, it looks better if you go alphabetically. Okay, x comes before y, m comes before n. Okay, all right, so as before, that means that our interval is going to be partitioned into sub-intervals from x0 to x1, x1 to x2, and so on. And of course, these xi's are all separated by delta x. Okay, so think of it as x0 plus delta x, and then x0 plus twice delta x, thrice delta x, and so on. Okay, similarly, our interval from C to D is partitioned into several subintervals, and the endpoints are C, and then y1 will be C plus delta y, y2 will be C plus twice delta y, and so on. Okay, so we have, here's a little piece of birthday cake. Okay, so we call this the subrectangle R sub ij. Okay, I going along the x, j going along the y. In the single integral, we picked an xi star on the x-axis. Okay, but now we have to pick a point pij somewhere inside this subrectangle. Okay, what are the ways to pick pij? Randomly, pick any point that you want, or you can pick the midpoint, find the midpoint of that rectangle, or you can pick the lower left endpoint, the lower right, the upper left, or the upper right endpoint. So many choices, okay? But it doesn't matter because we're going to take a limit. All right, so before we go on to the next page, there's one more piece here that we can explain, and that's this dA symbol. Okay, so in the single integral, we started with a delta x and it turns into a dx. Okay, so similarly, we will have a delta a, which is going to be the product of delta x and, oops, delta y right over there. Okay, so we have a delta a, this product, and that delta a is going to turn into our dA. Okay, so now let's scoot down over here where we complete the construction of the double integral. Okay, so here's the symbol for our double integral. It's going to be a double limit. Okay, there are two variables that are going to go to infinity. M and n, the number of pieces along the x-axis, and the y-axis, both of them have to go to infinity so that our pieces get smaller and smaller. Okay, and then we have a double sum. Okay, I will be for x and j will be for y. Okay, we plug in the points that we picked into our function, and then we multiply that by delta a, which was our delta x to delta y. Okay, and of course that delta a becomes dA in our symbol. Okay, so of course that double limit is the problem. Okay, how do we find that double limit, right? So we're going to find out that we don't have to worry about this so much because we're going to have a computational method by which we look for something like an antiderivative, plug in endpoints, something very similar that we saw in basic calculus. So I'm going to take you now to GeoGebra, and we're going to visualize exactly what this all means. All right. Now, we are in GeoGebra, but this is an app created by my dear friend and colleague, Professor Israel Castro at Pasadena City College. So you can change the function that we have up here, and you can change your domain. Okay, so you have, it looks like an elliptic paraboloid. Okay, so there it is. Ooh, yes, let's check it out. From above, we get ellipsis, and we have a domain. So x min, x max, that's your A and B. We're going from -2 to +3. Okay, y min, y max, that's your C and D. So we're going from -3 to +2. So if you look from above, okay, there's our domain. Okay, it is a square, 5 along each direction. Okay, we have these m and n, right? So these are what we call sliders, okay? And you can change the values of m and n, and the diagram will adjust itself accordingly, okay? So right now, we are subdividing x into 3 pieces and y also into 3 pieces. So we have these 9 subrectangles, which happen to be squares, okay? So notice that the app is creating these boxes, okay? So those boxes represent the value, the height of those boxes represent the value of those functions, of that function, at the representative points, okay? And I must admit, it's not very clear to me which point the app is using to get the height of these boxes. But it is a point somewhere inside the subrectangle. Okay, so this box we can clearly see because it's right in front. And yeah, the height seems to be determined by this corner of the box. Okay, so the nice thing is that we can increase the number of partitions along each axis. So we can just increase m. And notice that n is not changing, so this width, which is along the y-axis, is not changing. So to change that, we also have to move this slider. Ooh. Ah, okay. So we now have 5 times 5, 25 subrectangles, still squares, like so, okay? And now notice that the boxes are starting to imitate the function. Okay, of course, the tops are still flat, and this function is obviously curved. So if you increase the number of subdivisions, 6, 7, 8, how about let's go to 6, 7, 8, 9, 10. Yeah, there's a delay because, of course, it has to recalculate. So notice how those boxes are getting closer and closer at the top to the shape of your elliptic paraboloid. Okay, so of course we can't go to infinity, but we can make these subdivisions smaller and smaller. In other words, make the number of pieces bigger and bigger. Ooh, check it out. It almost looks like architecture, right? I can live in a building like that. 12. See, it's slowing down because, of course, it has to print those boxes. All right. So I hope this convinces you that as m and n go to infinity, the heights of those boxes more closely approximate the actual volume under that surface over the rectangle which is controlled by this domain. Okay. Speaking of which, we can change this. We can go, let's say, just from -1 to 2. And there it is. It does take a little while to recalculate. Okay, so what we're going to do next is we're going to approximate the value of a double integral. In our PDF, the function is e to the -xy. Okay, and the domain is from 1 to 4 and from 0 to 2. We are going to change that just a little bit so that you have something similar to compare it to. All right, so here is our example for the day. We have the function e to the -x over y. So I believe in the PDF we have e to the -x times y. All right, and let's make sure that we don't divide by 0. Okay, so y will go from 1 to 4. X will go from 1 to 3. There's no issue with x, it's in the numerator. Okay, we are going to use 4 subdivisions along the x-axis and 3 subdivisions along the y-axis. Okay, use those approximations, use those subdivisions to get an approximation for this double integral. Okay, so let's start with getting delta x and delta y. Okay, so delta x is fraction. Yeah, I don't think you've seen this toolbar before. So we have 3 minus 1, and then we want 4 subdivisions. Okay, so I do believe that is 1/2. There it is. Okay, and then we have delta y. So delta y is 4 minus 1. I think I'll just copy this. 4 minus 1, and the number n is 3, so that's just equal to 1. Okay, so that is our delta x and delta y. Now, we will partition our x coordinates into pieces of width 1/2. Okay, so our x0 will be the left endpoint 1, and then our x1 will be 1 plus 1/2. So 1.5, and then x2 will be 1 plus twice 1/2, or 1.5 plus 1/2. So that's just 2. x3 is, add another delta x, 2.5, and x4 is going to be 3. Okay, so notice that we wanted 4 subdivisions, and this is why we start at x0, not x1. Okay, so that we end with 4, which is our n. x4 is 3, the right endpoint. Excellent. All right, so similarly, we want to subdivide our y's. So our y0 will be the left endpoint for y, which is also 1. And we will add delta y, which is 1, to get y1 will be 2, and y2 will be 3, and equals 3, and y3 scoop will be 4. Okay, so there you go. You want 3 subdivisions, and so we end at y3. Okay, start at y0, we will end at y3. Okay, let's go to GeoGebra so that we can visualize exactly what we're doing over here. All right, so our rectangle is 1 to 3 along the x, 1, 3, and 1 to 4 along the y, 1 to 4 along the y. Okay, so let me tell you about the polygon command, which is right here. Okay, So we can create a polygon, but we need our brains to find the corners. Okay, so both intervals start at 1. So 1, 1 is our first point. And then on the x, we go to 3. So go to the right up to 3, and then click again to create the next point. Y will go from 1 to 4. So we have to go up to 4 over here. Haha. And then we complete the rectangle at this point. And click. There you go. Whoops. Okay. You just stay there. All right. Okay, we have to go one more down to point A. There you go. So that completes the polygon. Okay, so don't just stop at the last point. You have to go back to your initial point. All right, so it does all of this automatically, and it also shows, gives them labels. Okay, so what were our endpoints? Okay, so we said 1, 1.5, 2, 2.5, and 3. Okay, so we can create those vertical lines. We already have x equals 1. So let's do 1.5. Okay, there we go. X equals 2, x equals 2.5. Okay, there you go. And then we are going to create our horizontal lines. And we said that we got y0 is 1, and then 2, and then 3, and then 4. Okay, so we have y equals 2 and y equals 3. Okay, we can see y equals 4. Okay, so I'm doing this because I want to show you what the subrectangles look like. So this is how each subrectangle looks like. Which representative point are we going to pick? Let's pick the midpoint. Okay, so we need the midpoint over here. Okay, where is that midpoint? Well, fortunately, we can tell it from the graph. Okay, so that looks like 1.25. Okay, and the y-coordinate looks like 1.5. Okay, so that point is 1.25, 1.5. Okay, similarly, where are we here now? That's 1.75, 1.5. Okay, so fortunately, all of these points have the same y-coordinate, and all of these points have the same x-coordinate. Okay, so once you find the midpoints along the x and the midpoints along the y, you've found all of the midpoints in the 12 subrectangles. Okay, and we're going to put them together in a nice chart, and we're going to perform our calculations back in Scientific Notebook. All right, so our midpoints are 1.25, followed by 1.75, 2.25, and 2.75. Okay, so notice that we have 4 midpoints. Okay, we'd better have 4 midpoints because m equals 4. Okay, and similarly, we should have 3 midpoints along the y-axis because n equals 3. Okay, so we get as our midpoints 1.5, 2.5, and 3.5. All right, so now we're going to create a table with 12 points. Okay, so we'll need 12 rows, and then we need the labeling at the top, and so we need 13 or 14 rows. Just 13 rows. How many columns? We need x, y, the function, and we want an approximation. Okay, so let's make 4 columns. Okay, so this will be our xi, this will be our yj, and we are going to create our function here. So e to the negative xi divided by yj. Okay, so when you're doing your homework, you can just call it x, y, e to the minus x over y. and we have our approximation. We're going to put it over there. Okay, so our endpoints were, or our midpoints rather, were 125, 175, 225, 275. Okay, so let me put those here. 1.25, 1.75, 225, and 275. Okay, there are 12 points. Okay, so these four are going to repeat 3 times. Okay, because the y's will be first plug in 1 and then plug in I'm sorry, the midpoints are 1.5, 1.5, 1.5, and 1.5. Okay, almost messed up that one. So we're going to need these. I believe I can copy those. Yeah, all right. But this time, our next midpoint is 2.5. So 2.5 there, 2.5 there, 2.5 there, 2.5 there. Okay, so finally, copy one more time down here. And our last midpoint is 3.5. Okay, now the grungy part. Okay, we have to plug in this point into our function. So we need e to the power negative 1.25 divided by 1.5. Okay, so this is why I'm showing you my menu over here. So that button lets me approximate. Ooh, so there's the answer. Okay, so that goes into that entry over there. Okay, so bite the bullet, get your graphing calculators ready, or just scientific calculator. We're going to do it 11 more times, okay? But we can do a little cut and paste. So we got 1.75 there. And who do we have here? That goes in here. Okay, next we got 225. So I think I'll copy this one because we got the 25 already there. And we get this answer. Okay, and then finally 275. So I'll copy this one and 275. Okay, we got this. All right, so we are going to have these 4 entries so far. Okay, now we all have our habits with our calculators, how we like to use them, okay? I would suggest though that you don't let things get too far ahead. If I were you, I would create these subtotals in groups of 4 as we have computed them, just so we don't have to recalculate all of these numbers all over again. Wouldn't that be a bummer? So add up those 4 numbers so far, and that's what we have so far. Okay, so we have to repeat it now for these other 8 values. Okay, you're probably not that interested to see me do that, so I will pause the video and I will fill in the numbers. You can also pause the video and fill in the chart on your own and compare your answers when we get back. Okay, I'll see you in 1 second. All right, here we go. So we have 8 more numbers over here, and I copied the answers down here so that we can get our 2 other subtotals. So I hope you got the same answers as I did. So those 4 numbers add up to that, and these four numbers add up to that. All right. So yeah, so look at the patterns. Okay, that is increasing, 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 increasing. Okay, because x is in the numerator, but of course as we go left to right, it's decreasing because y is in the denominator. Okay, so hopefully we didn't make a mistake with any of these numbers. Now we get the grand total. Okay, so the first four plus the next four, and then the last four. Like this, and again, it really depends on you how you add this up. You can use your memory button. You can just keep on adding the next number. Anything you want. All right, so the total of all 12 is 5.259. Okay. However, okay, let me take this total over here. Let's scoot back up here. Okay. Let's not forget that we have a delta x, delta y. All right. So this integral that we want is, let me paste that answer that we got. So therefore, the integral that we want is going to be approximately, I do have a symbol for approximate. And there it is, right there. Okay, so that's the total of those 12 answers times delta x, delta y. Okay, so obviously we don't have to put in the 1, but we have to divide by 2. Okay, so our integral is approximately 2.63. Okay, now let me show you, because yeah, we have some time. I have the integral symbol right here. Okay, so Maple does allow you to compute single and double integrals and so on. Okay, so here's the syntax. You need the integral symbol, the function goes in there, and then what we're going to do is what's called an iterated integral. Okay, we're going to see this in the next video. Okay, we can, since we have 1 to 3 for the x, the differential there should be dx. Okay, so now repeat it for the y. We need 1 to 4. Okay, so I'll copy this, change that 3 to 4, and then the inner differential is the dy. Okay, something to look forward to. Our function goes in here, so we have e to the negative xy. Okay, let me save this just in case it blows up. Okay, let me also pause the video. Okay, I do that so that in case I mess up, I don't have to correct everything up to the last 5 minutes or so. So, I want to show you something. This button is for exact, evaluate exactly, and this is to evaluate numerically or approximately. Can we get an exact answer? What happened there? Oh, nothing. Basically, Maple gave the problem back to us. And it's like, don't even. Okay. So, it turns out that, yeah, you can be super smart and spend days and weeks trying to find an antiderivative that works. I haven't even explained to you what we're supposed to do, calculus-wise. Not going to work. Okay, so we will never get an exact answer for this integral. But let's see what Maple says. Okay, what is your numeric answer? Ooh, 2.617. Not bad. We have 2.629. We're not that far away, right? It's like 0, 1 in difference. 0, 1, 2, something like that. Okay, but of course, that's because our m and our n are very small. Okay, just 4 along x, 3 along y. Okay, so imagine if it were 40 and 30. Imagine that, and imagine how big your table is going to be. right? You're going to have 1,200 entries. Yeah, I'll see you in a few days. No, just kidding. So yeah, obviously this is a kind of integral that, yes, well, we're not going to have too high expectations. Okay, this approximation that we got is good enough. Okay, so in our next video, we are going to see something that looks a little bit like the fundamental theorem of calculus that will allow us to find exact values for certain double integrals if you can find some kind of an antiderivative. Okay, so all will be explained in our next video. So until then, I hope you enjoy the rest of your day, and I will see you very soon. Bye.